Assalamualaikum. Welcome to this video on graphs. What is a graph? A graph consists of vertices, which can be considered as sites or locations, and edges, which represent connections between vertices. Let's look at this sample application. It is an air flight system where each vertex represents a city and each edge represents a direct flight between two cities. Let's say you are wondering, is it possible to go from London to Moscow? The real question is, does a path exist between London and Moscow? If each edge is marked with a value that represents the number of hours to travel from cities, and say you're wondering which path is the fastest to go from London to Moscow, it is about calculating the total weights for each possible path and determine which one is the lowest value. So basically, a graph is specified by the ordered pair V and E, where V is the set of vertices and E is the set of edges. There are several ways to classify graphs. First, we have undirected and directed graphs. Next, we have unweighted and weighted graph. Finally, we have disconnected and connected graph. These are examples of weighted graphs. For an undirected graph, each edge connects two vertices without any particular direction. So, an edge AB can also be specified as BA. For a directed graph, however, the direction is only one way. For example, from A to B, but not from B to A. There are two possible ways to represent a graph. First is adjacency matrix. The other is adjacency list. First, see how we represent a graph using adjacency matrix. The matrix requires a two-dimensional array of size n by n. By assigning the index value for each vertex ID, the first edge that connects between vertex A and vertex C, we can describe it as A is connected to C and C connected to A. And we'll do the same for all the other edges. After we have assigned value 1 for all the connected edges, the rest of the cells are filled with zeros. For an unweighted graph, the value 1 is used to mark when two vertices are connected. For weighted graph, on the other hand, the weights for each edge is used instead of 1. Next, let's look at adjacency list. We start by having a one-dimensional array of size n. For the edge that connects vertex A and vertex C, we add linked list items from A to C and from C to A. We repeat for the other edges one by one. This is the completed adjacency list. So this is another example of a graph and its adjacency matrix, and the same graph with its adjacency list. If we compare between adjacency list and adjacency matrix, adjacency matrix will require more space, but we can quickly determine if two vertices are connected, while an adjacency list requires more time to find if an edge exists, but the storage is more compact. That's the end of the video. Have a nice day.